In this lecture, we will talk about the natural response over an example. Okay. First, we begin by defining a natural response. In fact, we already talked about it in the past, so let's remember what it is. Natural response is what you observe in a circuit that's driven only by the initial conditions. That means you have no inputs in the circuit, or perhaps you do, but you kill all the independent voltage sources and independent current sources, and you're interested in, you're observing the response due to the initial stored energies in your dynamic components. Okay, so natural response is the response of a circuit, okay, or a solution of a circuit to initial conditions only. Okay. In other words, it's another name for zero input response. Okay. So let's consider such an example where we have no external inputs in our circuit, and let's consider the following simple but not too simple to be interesting example. So we have 3 capacitors and 2 resistors connected as shown. All the capacitors are of unity capacitance, and we have 1 ohm for both resistances. Let this be our first capacitor and its voltage is denoted by V1, and let this be our second capacitor and its voltage is denoted by V2, and we let this be our third capacitor, okay, V3. So for this example, given that V10 is something, okay, V10, and V20 is something else, which is denoted by capital V20, we are asked to do the following. Write the node equations. Okay, so we will obtain the formulation through node voltages for this circuit, and what we will do next is something that we haven't done before, namely, once the formulation is obtained, we will try to solve the circuit, and in this case it's finding the voltages V1t, V2t and V3t, all the capacitor voltages. Note that we have 3 dynamic components in our circuit, 3 capacitors, but this circuit is only of order 2. It's a second order circuit because the initial conditions, once you choose the initial conditions V10 and V20, V30 is automatically fixed. Namely, the degree of freedom in choosing the initial conditions for this system is 2. Therefore, despite the fact that we have 3 dynamic components, we have only a second order circuit. Okay. So let's begin our solution A. In order to begin writing node equations, what we do is we have to do the proper labeling. So that's our first step, or even 0th step. So what we do is we choose a node, ground node, and then we label properly the remaining nodes. Let's call this node voltage E1, and let's call the voltage of that node E2. Okay. Now E1 is clearly no other than V1, and E2 equals V2. Okay, and this is our ground node. Now what we're going to do is we're going to write KCL in this equation, in this node, and KCL in that node, and we will try to express everything in terms of our formulation variables, which are E1 and E2, and then finally we're going to put them in matrix form. Okay, and then once we have that formulation, we will start thinking about how we can solve that equation, that formulation. Okay, so let's begin by node 1. Okay, so we have this current plus that current equals 0 by KCL. This current is C1 dV1, is the capacitor current. V1 is E1 and C is 1, therefore we have dE1, okay, for this current. And then we have this E1 over the resistance, which is 1, and finally we have C3 dV3, this current. V3 is E1 minus E2 and C3 is 1, therefore we're talking about dE1 minus E2, and that by KCL should equal 0. Okay, as for the second node, we're going to do the same thing. Okay, this current is dE2 plus we have the current through the resistor E2 over 1, and finally we have E2 minus E1, and that equals 0. Because of the symmetry of the circuit, we have a nice symmetric pair of equations. Okay, now let's collect these two equations and put them into a single equation, single matrix equation. And that equation we're already familiar with, and it will have the following form. Okay, some 2 by 2 matrix, because we have two formulation variables, which we have previously called node admittance matrix, multiplying the vector of unknowns or formulation variables. In this case, they are node voltages E1 and E2, and that equals the right hand side, and the right hand side consists of the inputs, okay, in the circuit, which we don't have any, plus the certain initial conditions if you have some integral terms. Again, for this example, we don't have any integral terms because we are formulating circuit through node voltages and we don't have any inductors in the circuit. In that case, no integral terms or D inverse terms appear. Okay, so that means the right hand side eventually should turn out to be 0. Okay, for the first row, let's look at the first equation. For E1, we have dE1 here. We have another dE1 here, so that makes 2 dE1, and we have just one E1 here, so that makes 2D plus 1 E1. And then for E2, we have minus d E2 here. And what remains, we throw to the other side. In this case, nothing remains, so that means the right-hand side is 0, as expected. Okay, do the same thing for the second row. Let's look at the second equation. For E2, okay, excuse me, for E1, we have minus d here. Okay, only for E2, d here, that makes 2d, and unity E2 here. So we can write 2d plus 1 E2. What remains, we throw to the other side. Nothing remains, meaning right hand side equals 0. So this is our E node voltage vector. Okay, so what we've obtained, therefore, is node admittance matrix multiplying the node voltage vector equals 0. And that completes our formulation of this simple dynamic circuit. Now, having formulated the circuit, now we can start thinking about how to solve it. And we need at least, well, in principle, we have everything we need, namely, we have the initial conditions and we have the differential equation. And once we have that pair of information, you should be able to obtain the answer. which must be unique because we're dealing with an LTI system. Okay, part B. Let's try to say something about E of t, E1 of t and E2 of t. Note that once we have E of t, in other words, once we have the node voltages, we can easily write down all the capacitor voltages, V1, V2, and V3, because V1 is E1, V2 is E2, and V3 is the difference between those two node voltages. Okay, now we begin by a guess on the form of E of t. Okay, now our guess is the following. Let's say E of t, first of all, E of t is a vector, okay, in R2. So our guess is that E of t, the solution, has the following form: some exponential. So this E is, okay, there's a slight risk of confusion here. This E is our node voltage vector. It's a variable. This E is the constant, okay, 2.71828. Okay, so please be careful there. So E to the st, S is some complex scalar constant, and this scalar is scaling a vector which also is constant, and we denote it by x, where S in C, S is a complex scalar and x is a complex vector, but both are fixed. Okay, now let's try to figure out the consequences of this guess. Okay, so assuming or supposing that E of t has this form, what can be said about this scalar S and this vector x? Okay, and for that, let's use the only thing that we have, and that's the formulation y of t equals z. So what we're going to do is we're going to take that guess and put it into equation and see what the equation will tell us. Okay, so the equation is, okay, let's swap the sides. 0 equals node admittance matrix times the node voltage vector E of t. Now we're assuming at this stage that this vector has this form, e to the st times the constant vector x. Now, the nice thing about working with an exponential function under differentiation is that it's very easy to take the time derivative of e to the st. It's simply multiplying by s, right? Therefore, this can be written as y of s. All these d terms will turn into s's, okay, when E of t has this form, and then we can write this as y of s times, okay, e to the st times x, okay. All the d's become s's, and then at that stage y of s, since s is a constant, y of s is also a constant matrix, and then we can, and this is a scalar, and we can carry it to the other side, okay, of the equation. In other words, this we can write as y of s times e to the st x, and e to the st can be easily put on the left hand side. So we can write e to the st y of s times x, and here what we used is the following: e to the st under derivative operator yields simply s e to the st. Okay. Now, this should equal 0. Here we have e to the st, s is some complex number, and we know that this is never 0. Therefore, we can cancel it and reduce the equation into y of s times x equals 0. Okay, y of s times x equals 0. So if our guess were correct, then it must be that our s and our x should satisfy this equation. Note that this equation is nicer, or at least simpler than this equation, because this is a differential equation, whereas this is just an algebraic equation. Okay, a constant matrix multiplying a constant vector. Okay, now how about the solution of this equation, which will tell us something about both on S and X. Now there is a trivial solution, which is x equals 0. In that case, it holds for any S. So that's a solution, but eventually that solution will not satisfy the initial condition constraints, plus it's an uninteresting solution. So let's consider the case where X is a non-zero vector. Okay. So if X is different than 0, then y of S times X equals 0 means what? Now, first of all, y of S is a 2 by 2 matrix. And here X is a vector of size 2. So what you're doing is you're multiplying a non-zero vector with a matrix, and the right-hand side is 0. So that means that that matrix must be singular. Okay. Ys must be singular. It should be non-invertible, in other words. And if a matrix is singular, and a scalar matrix, square matrix is singular, so that it means that it should have an eigenvalue at 0, and that means its determinant must be 0. Okay. So determinant of y of S equals 0. So we reached a very definitive information regarding our guess. Okay, it says that if E of t has this form, then S cannot be an arbitrary scalar. It must satisfy this equation: determinant of y of S equals 0. Okay, so let's compute that determinant. Okay, determinant of y of S, which will give us a second order polynomial in S. And try to figure out the roots of that polynomial, which would be the solution of this equation. Okay, determinant of y of S equals the following determinant: 2s plus 1 minus s minus s 2s plus 1. Okay, so that's 2s plus 1 square minus s square, and that equals what? 3s squared plus 4s plus 1. Okay, a second order polynomial which can be factored into 3s plus 1 times s plus 1. Therefore, if this determinant equals 0, it's possible only for s equals minus 1/3 and s equals minus 1. Okay, so that means if this guess is correct, then s cannot be an arbitrary scalar. It can either be minus 1/3 or minus 1, which is a very nice piece of information regarding our guess. Therefore, determinant y of s equals 0 implies s equals minus 1/3 or s equals minus 1. Okay. Having figured out two possible values, only possible values for s, let's also try to say something, if we can, about x. Okay. But before that, let me put this remark down. Those two numbers are not arbitrary numbers. They're important for the circuit. Therefore, they have given names. In other words, they are the natural frequencies of the circuit. The roots S1 equals minus 1/3. Okay, so without loss of generality, let the first root be minus 1/3. S2 equals minus 1 are the natural frequencies Sometimes they're called the modes of the circuit. Okay. Now, let's suppose that S equals minus 1/3. And then, under that assumption, we will try to figure out certain things about X. S1 equals minus 1/3. So, if our guess is correct and if S equals minus 1/3, then the associated solution E of t equals e to the S1t times x. And x is a vector of size 2. The question is, what can be said about x? Can it be an arbitrary vector? It turns out that it cannot be arbitrary. It has to belong to certain subspace of the complex plane C2. Solve y of s. Remember that we obtained the equation y of s times x equals 0, and now we're working with some particular s, and that s is minus 1/3. So therefore, let's look at the equation. S equals minus 1/3, okay, times x equals 0. So this means that x cannot be arbitrary. X must belong to the null space of this matrix that you obtain when you plug in s equals minus 1/3. So, when s equals minus 1/3, you have 1/3, 1/3, 1/3, 1/3 for y of s. Okay? Well, in our case, s is minus 1/3. Minus 1/3. Times x equals 0. Therefore, x must belong to the null space of this matrix, which is not difficult to see that x must be of this form, okay? 1 minus 1 multiplied by some constant. For any such constant, C1, such x will be in the null space of this matrix. In other words, it would satisfy y of s times x equals 0 for s equals minus 1/3. Okay, where C1 is any constant. Okay, well, eventually we will, when we apply the initial condition constraint, we'll see that it cannot be any constant, but it should be some particular constant, and that particular constant will be determined by the initial conditions. But for now, we're not caring about the initial condition, okay? We're only dealing with the differential equation, and as far as the differential equation is considered, okay, this x works just fine. Okay, so let's write finally the node voltage. E of t must equal some constant times this vector, which belongs to the null space of this matrix, times e to the minus t over 3. Okay? So, for any C1, this node voltage vector will satisfy the node equation. So that's what we will obtain. Now, remember that we have another possibility for S, namely S equals minus 1. Okay, S2 equals minus 1, the second natural frequency. Now, we follow the same procedure here, and this time we obtain following. E of t for that s should have the following form, some constant which we call C2, 1 times e to the minus t. This 1 vector is a vector that belongs to the null space of y of s when s equals -1. Okay. So let's also put it in a box. Now this solves our homogeneous differential equation, namely node equation. Why homogeneous? Because we don't have any input in the circuit. This too solves our node equation. And since we're dealing with an LTI system, we can apply superposition. So that means any linear combination of these two solutions must itself be also a solution. Okay? And that takes us to the general form of solution for our circuit. Hence, the general form, the solution, reads E of t equals C1 1 minus 1 e to the minus t over 3 plus the second piece plus C2 1 e to the minus t. Okay, this is, let's call it equation star. And this node voltage will satisfy the node equation. So that's what we've obtained. So let's write that down. For any C1, C2, the node voltage obtained in equation star satisfies the node equation. Which was node admittance matrix times E equals 0. Okay. Now, since for any C1 and C2, this equation is satisfied, clearly we cannot use this equation to figure out the exact values of C1 and C2. So what we have to do is we have to use something that we haven't used, use some constraint we haven't used. And the constraint that we haven't used yet is the initial condition constraint. Okay, so let's do that. What's C1 and C2? That's our next question to be answered. Apply initial condition constraint. Okay, so let's do that. What's the initial node voltage vector? So that's by definition E1 0, E2 0. And then remember the circuit. First node voltage was the first capacitor voltage, and similarly for the second node voltage and second capacitor voltage. And these two pieces of information we're given. Okay. As V1 0 and V2 0. Let's say 6 volts and minus 13 volts. V2 0. Okay, so this is the so-called initial condition constraint. E of 0 equals this vector, which is given. Okay. So this solution, therefore, must simultaneously satisfy star for C1 and C2, and also double star, this equation, initial condition constraint. So if we combine those two equations, star and double star, C1 and C2 should automatically appear, because there's nothing else left from the constraint point of view to apply on our candidate, E of t. Star and double star implies what? So plug in t equals 0 here. E to the minus t over 3, this is 1, this is also 1. So what we have is e to the 0 vector, which is this, v1 0, v2 0, equals c1 times this vector plus c2 times that vector. Now c1 times this vector plus c2 times that vector can be written nicely as some matrix multiplying the vector of unknowns, which is the vector of c1 and c2. So 1 minus 1 1 1 times c1 c2. Okay, so note that this is c1 times this first column plus c2 times the second column. This is the first column, this is the second column, and this equals what? E0, and E0 equals v1 0, v2 0. Okay, hence c1 c2 equals 1 minus 1 1 1 inverse. We multiply both sides with inverse of this matrix times v1 0, v2 0, and the answer turns out to be 1/2 times the difference and the second entry is the average of two initial voltages. Okay, now C1 and C2 are also known. That means everything is determined, and we can write down the solution. I'm using the article D because we're talking about an LTI system for which solution always exists and unique. Okay, so let's write down our final answer. E of t, node voltage vector, equals C1 times, which now we know equals this, the vector 1 minus 1, and that's multiplied by e to the minus t over 3, plus C2 times, which is v1 0 plus v2 0 over 2, 1 1 e to the minus t. Okay. And this is the solution of our node equation. Okay. And finally, let's write down all the capacitor voltages. V1 of t is E1 of t, okay, which is the first entry of E of t. In other words, 1 0 times E of t. V2 of t is the second entry of the node voltage vector. In other words, 0 1 times E of t, and V3 of t is E1 of t minus E2 of t. This is the third capacitor voltage, which equals 1 minus 1 times E of t. Okay? And this equals what? Now, let's concentrate on the third capacitor voltage. Now, what we're doing is we're multiplying with this row vector, 1 minus 1, this vector E of t. Now, since 1 minus 1, this row vector is orthogonal to this column vector 1 1, this times that equals 0. And no matter how you choose the initial condition, no matter what C2 is, this product will always give you 0, and that means e to the minus t term, that mode will never appear in the third capacitor voltage, no matter how you choose the initial conditions. Okay, and indeed we have this for V3 of t, whereas for V1 and V2 you see that we have both this and that terms appearing, both modes appear for an arbitrary initial condition, for general initial condition. Okay, Now this finishes our example, but before we close, let's make certain observations, okay, which are important in general, not just for this example. Okay. Mode s equals -1 does not appear in v3t equals v10 minus v20 e to the minus t over 3, regardless of how you choose the initial capacitor voltages. In general, not all modes appear in every branch voltage or current. Okay, and that's a very interesting and also important subject, which is studied in detail in graduate courses under the title of observability, okay, in linear systems. Second, okay, observation is the following. Note that for V3, okay, no matter how you choose the initial conditions, this mode will never appear. So that's a particular output for the system, particular branch voltage. Now we're going to talk something more general about a mode disappearing from the entire circuit. Okay. Now for this case, the mode at -1 or e to the minus t mode, it disappears only from one branch voltage, and that disappearance is there regardless of how you choose the initial conditions. Okay. And now if you ask the question, can I choose the initial conditions such that a mode, either s equals -1/3 or s equals -1, disappears from the entire circuit, okay? And it's easy to see that. You can do that if you choose very carefully your initial conditions. For instance, if you choose the initial capacitor voltages equal to one another, V10 minus V20 is 0, and e to the minus t3 term, or the term corresponding to mode at s equals -1/3, disappears from the node voltage vector. If it disappears from the node voltage vector, it means it disappears from the entire circuit. Likewise, if you choose V10 equals minus V20, like 6 volts and -6 volt, then this mode, s equals -1, disappears from the entire circuit. Okay, so let's also write that down by adjusting the initial condition such that V10 equals V20. We can make the mode S equals -1/3 disappear from the node voltages E1 of t and E2 of t, and as a result from the whole circuit. Okay. In other words, by choosing initial conditions equal only the mode s equals -1 is set to be excited. Okay. Now this is the case for choosing equal initial conditions, which makes this mode disappear. Clearly, you can also choose the initial conditions with equal magnitudes but opposite sign. In that case, this mode disappears. So what we have written down should also hold for the other mode, namely v10 equals minus v20, s equals -1. Okay, disappear, and v10 equals minus v20, only the mode s equals -1/3 is excited. Okay, so what we said for one mode clearly holds also for the other mode.